Now that we have this notion of definiteness of quadratic forms at our disposal, let's see if we can't use some techniques from linear algebra to actually calculate the definiteness of a quadratic form. Remember, the guiding example here is this last example from the previous video, where we had a quadratic form on 3 variables, and we realized pretty quickly that actually calculating the definiteness here is somewhat hopeless if we're just using our brains, or at least if we're just trying to eyeball the example. So here I want to start by showing that we can use some of the ideas of linear algebra to represent any quadratic form. So here we have a quadratic form on 2 variables, and the formula is negative x squared plus 6 times xy plus 6y squared. And all I want to point out here is that the data in this quadratic form can be organized into a product of matrices. So what is the product of matrices we're looking at here? Well, I'm looking at the variable vector xy as a row. Then I'm looking at a 2 by 2 matrix whose entries are -1, 3, 3, and 6 in the columns. And then I'm multiplying by the column vector of variables xy. We'll say in a moment where we got this 2 by 2 matrix from, but for now I just want us to look at this product and see what happens when we multiply everything together. So maybe I'll start by taking this 2 by 2 matrix and multiplying by the column xy. When we do that, we get a vector, and that vector has coordinates -x plus 3y and 3x plus 6y. Now we want to take that column vector and multiply on the left by the row vector xy. And when we do so, we end up producing -x squared plus 6 times xy plus 6y squared. This is exactly the formula for the quadratic form that we defined previously. So it appears with this example that we can study this quadratic form by maybe representing it as a matrix product. And since we know a lot about matrices, maybe our knowledge of matrices will help us understand this quadratic form. One last thing I'd like to point out in this example is that when we represented our particular quadratic form here as a matrix product, the 2 by 2 matrix that popped out in the middle was a real symmetric matrix. And we know that every real symmetric matrix is a Hermitian matrix, and therefore the spectral theorem can be used to study that matrix. Okay, so this is exactly what ends up happening in a general example. So let's say that the formula for our quadratic form is the sum of a bunch of terms of the form xi times xj, where I and j could possibly be equal, and that the scalar we're using to multiply xi times xj by is given by c sub ij. In other words, let's say that we have our formula for the quadratic form, and we know what all of the coefficients in all of the terms are. Well, let's look at the formula, and then let's define a matrix called S. The matrix called S, I like to think of as being a square matrix, where I like to index each of the columns by the variables x1 through xn, and then I like to index the rows the same way, by the variables x1 through xn. So the data on top and to the left of this matrix is not contributing to the formula for the entries in this matrix. I just like to use them as a guideline when I'm thinking about constructing this matrix. So here's the idea. We can fill in the diagonal of this n by n matrix by just plucking out the I coefficients in the quadratic form. And these are exactly the coefficients on front of the squared terms. Then we look at all of the off-diagonal positions. And let's say in this 1, 2 position, what we'll do is we'll look at c sub 1, 2, which is the coefficient of x1 times x2, and then we chop it in half. And then we pair that position with the 2, 1 position, and we insert the other half of that coefficient. So essentially what we're doing to construct the 1, 2 position inside of this matrix and the 2, 1 position is we're looking up the coefficient of x1 times x2 in the quadratic form, and then we're chopping it in half and putting half in the 1, 2 position and half in the 2, 1 position. And we continue this process for every off-diagonal entry in this matrix. The idea is that when we're done looking at all of the coefficients, we have filled in an n by n Hermitian matrix, and the quadratic form now takes on a special formula. The quadratic form takes on the formula Q of an input vector x is the same thing as the inner product, and if we're using real entries here, the inner product is the same as the dot product of the variable vector x with our new matrix S multiplied by the variable vector x. So let's see this in an example. Here we have a complicated quadratic form on 3 variables, and the formula is -3 times x1 squared plus 6 times x1 times x2 minus 10 times x1 times x3 plus x2 squared minus 12 times x2 times x3 plus 7 times x3 squared. So someone is handing us this quadratic form, and what we want to do now is we want to represent this quadratic form with a Hermitian matrix according to the formula from the previous slide. So the idea is that the formula for the quadratic form can neatly be written as the inner product of the variable vector x with s times the variable vector x, and all we need to do is fill in all of the missing entries in our matrix S. Since this is a quadratic form on 3 variables, our matrix S will end up being a 3 by 3 Hermitian matrix. Let's carefully input each of the missing 9 entries of this 3 by 3 matrix. So let's go term by term here. The first term in this quadratic form is -3 times x1 squared. So how is this -3 as a coefficient going to be inserted inside of our empty matrix? Well, we're looking at the x1 entry in this matrix, which is really just the 1, 1 entry. And that's on the diagonal, so what we do is we just take out -3 from the quadratic form and place it in the 1, 1 position on our matrix. Okay, let's move to the next term. The next term is 6 times x1 times x2. So now we're looking at maybe the x2, x1 position in our matrix, which is the 2, 1 position in our matrix. And the formula from the previous slide says we should take our coefficient 6 and then divide it into 2. So, or divide it by 2. Well, 6 divided by 2 is 3, so we should put a 3 in the 2, 1 position. But the 2, 1 position is paired with the 1, 2 position, where we should put another copy of 3. Great. Now let's move to the next term, which is -10 times x1, x3. Let's start by taking this coefficient and dividing it by 2 and placing it in the 3, 1 position in our matrix. So -10 divided by 2 is -5. So we'll start by putting a -5 in the 3, 1 position. Then we'll take the other half of -10 and put it in the 1, 3 position. So another -5 goes in the 1, 3 position of our matrix. Our next term is x2 squared. So the coefficient here is 1, and x2 squared is x2 times x2. So we're looking at the 2, 2 position in our matrix, and we're just going to put in 1 as that entry. Remember, for the diagonal entries, we're not dividing by the coefficients by 2. Great. Our second to last term here is -12 times x2 times x3. So we're going to divide -12 by 2, and then put the first half of -12 in the 3, 2 position. So we get a -6 in that position. Then we put the other half of -12 in the 2, 3 position, which so we put a -6 in the 2, 3 position of our matrix. Our last term in the quadratic form is 7 times x3 squared. So let's take that 7 and place it in the 3, 3 position of this matrix. So 7 goes in the last missing entry of our 3 by 3 matrix. And now we're done. We've gone through every term for our quadratic form. We've located that coefficient or that in the quadratic form, and we've appropriately placed it in our 3x3 matrix. Now that we're done filling in the 9 entries of this 3x3 matrix, we again see that this is an example of a 3x3 real symmetric matrix, and therefore this is a Hermitian matrix, so the spectral theorem would apply, for example. Another example I want to illustrate is that let's say that we already had the matrix that we were studying, and let's say that the matrix we were studying happened to be a diagonal matrix. So let's say that D was lambda 1, lambda 2, down to lambda n on the diagonal of an n by n matrix. And let's say that we defined a quadratic form by the formula variable vector x inner product with this matrix D times the variable vector x. Well, we can already predict what the terms of this quadratic form will be. We only have entries on the diagonal, and we don't have any entries on the off diagonal. This is telling us that what we're really doing is we're multiplying every choice of a variable twice by one of these lambdas, and there won't be any other terms. So here, the formula for our quadratic form should be q of x1, x2 up to xn equals our first diagonal entry, lambda 1, multiplied by our first variable squared. Then the next term will be our second diagonal entry, lambda 2, multiplied by our second variable squared. And we keep going until we get to our last diagonal entry of our matrix, multiplied by our last variable squared. So the moral here is that diagonal quadratic forms have no cross terms. So in our scenario here, there aren't any x1 times x2 terms, or x2 times x4 terms, or x3 times x6 terms, and so on. We only have square terms when the matrix representing our quadratic form is a diagonal matrix.